All right. All right, in chapter 29, we start with what we talked about in chapter 28. I said that chapter 28 is about what the magnetic field does to a moving charge or a wire having current in it. But in 29, it is the sources of magnetic field, which is, how the magnetic field is created. And I briefly talked to you about how the magnetic field is created. We said a moving charge Q that moves with the velocity v, creates a magnetic field that's given by this equation at any point in space. And the magnetic field looks like this, as around circulating around the velocity vector. And if you look from behind, you see that it's a circulating magnetic field. Means that at any point, see at this position, magnetic field is tangential to this circle and in this direction that you see. And then we said that a current element, an element of a wire, the DL of a wire that has a current I passing through it, it creates a magnetic field that's exactly similar to the magnetic field of a moving charge by just replacing IDL, replacing QV by IDL, which is, I showed you how they are equivalent to each other. Is the I is Q over T, V is DL over T. So it depends on whether you look at the Q divided by T or DL divided by T, which is the velocity. So you can write in two different ways. This is called Biot-Savart's law. And again, when you have a current element, looking from behind, the current is going into the page. It creates a magnetic field that's circulating around it, exactly like this, coming from right-hand rule. All right, and then now we're going to talk about if you have a line segment that has a current I in it, and you want to calculate the magnetic field of this line segment at distance r from one end, perpendicular distance r from one end, what is the magnetic field here? Again, from the right-hand rule, you see that the magnetic field, I hope you are able to do that. If you put your thumb in the direction of the current in the loop, in the wire, your four fingers show circulating in coming out of the page above the line, going into the page below the line. So at point P, the magnetic field is going out of the page, and it will be given by this mu naught I over 4 pi r sine theta. I can do integration and show that, but because we don't have a lot of time, I don't want to go through a lot of calculations here. And if you have a long straight wire, then you have this side going to infinity. So this angle theta becomes what? Goes like this, it becomes 90 degrees, and sine theta becomes 1, right? And then that's for half a line. If you have another half semi-infinite line on the other side, you have a total infinite line, and the two magnetic fields add up because they are in the same direction at this point. So you see that sine theta becomes 1. So you have 2 of mu naught I over 4 pi r becomes mu naught I over 2 pi r. So this is the magnetic field of a long straight wire. And again, if you can see that from right-hand rule, the field is circulating around it, and it looks like this. So above the line, it's coming out, the magnetic field is coming out of the page. Below, it's going into the page. And here, of course, it's going down into this plane. So this three-dimensional figure shows the magnetic field. You can imagine it like that. All right, any questions so far? All right, now we want to study magnetic force between two long straight parallel wires. This is very important because it makes you understand why the opposite poles of magnets attract each other and like poles repel each other. All right. So hardly anybody knows exactly how that works, and I'm going to explain that. So we're going to consider two long straight wires. One has current I in it, one has current I prime. And we want to see what kind of forces these apply on each other. To begin with, we said that each one of these currents create a magnetic field in the position of the other current. And that other current in the magnetic field produced by the first current is experienced as a force. All right, so we're going to derive these forces, see what direction they are. So to begin, we say, what is the direction of the magnetic field of the lower wire I at the position of the upper wire I prime? So we want to see what is the magnetic field of this one, the lower one, at these points that the other upper one is positioned. So, oops, did I just, sorry, I clicked on the wrong place. And so I want to launch the polls and I want your answers, okay? Very simple. What is the direction of the magnetic field of the lower wire at the position of the upper wire? It should be a quick one. All right. We have about half of you answering. Okay, we need a few more if you want. I'm going to end it soon, so, and the answer is quick. So I see that about 1/3 of you answered correctly, and here is the result. So the ones who say, okay, because the current is going to the right, the field is to the right, they're not paying any attention to what we are saying. All right, so forget about those. The answer out of the page is correct because of the right-hand rule, okay? So we said that you put your thumb in the direction of I, and then your four fingers show the direction of the circulating field around it. So above it, it's going out of the page. In below it, it's going into the page. All right, so here is the field if I want to show it. It's out of the page, therefore it is shown by dots. All right, and now we want to see what is the direction of the magnetic force on the lower wire, on the upper wire. It should be upper wire, I prime on the, oh, sorry. What is the direction of the magnetic force of the lower wire on the upper wire? So now we have a magnetic field around this current. What is the direction of that force acting on that wire? So I'm going to launch that again. And you answer this. You know what the magnetic field of, what the force of magnetic field is on a current. I hope you remember that. It is IL cross B. All right, I think we have all of the different answers. Let's see if it breaks toward the correct answer. All right, so 60% of the answers are in. Anybody else? I think that's all we get, 70%. And the poll. All right, so share the result. Let's see how you did. So it's pretty much even for every answer. So this is hopeless. I'm not going to ask you anything else. I just do my job and tell you because it doesn't make a difference apparently. So the answer, we said that if you put your 4 fingers in the direction of the current and then turn into the magnetic field, which is out, so you see that your thumb shows down. So the answer is downward. So out of 16 people, only 4 answered correctly. That's 1/4 of all the answers. All right, so the answer is down. And then if we do for the other one, you see this is the way it works. The magnetic field is this way, and the force is toward the lower one. This is the 3-dimensional perspective of that. And then what is the direction of the magnetic field of the upper wire at the position of the lower wire? I'm not going to waste time. So the upper wire creates a magnetic field in the vicinity of the lower wire. And according to the right-hand rule, if you put your thumb in the direction of I prime, you see that circulating, coming out above it, going into the page below it. So it is going to be into the page. And then the magnetic force acting on the lower one due to the current I prime is L cross B. Again, you put 4 fingers in the direction of L, turn into B, your thumb shows up. So shows up, this will be the force. So that means that when you have the 2 currents parallel, the 2 currents attract each other. And then this is the same as that again. And you can also calculate the magnetic force per unit length, because the magnetic field of one of them is mu naught I over 2 pi r times the other one, I L cross B, per unit length will be B times I prime, with B of I times I prime. And the angle is 90 degrees. So you get mu naught I prime divided by 2 pi r. This is the force per unit length of these 2 attracting each other. And then what if the currents are opposite of each other? If the currents are in opposite, the magnetic field of this one in here is out of the page. And then you see that the force on this one, because the field is out here, the force is up. And for the other one, the magnetic field of the upper one in this vicinity is also out of the page, because you put your thumb in the direction of I prime now, your 4 fingers show the direction of the magnetic field, which is out, and the magnetic force on I now due to I prime is downward. And then so you see that if the 2 currents are in the same direction, they attract each other. If 2 currents are in opposite direction, they repel each other. So currents in the same direction attract, currents in the opposite direction repel. That comes from those basic principles that we say how the magnetic field is created and how a moving charge in a magnetic field experiences a force. So there are 2 basic equations. And now we want to see why the like poles of magnets repel and opposite poles attract. This is a magnet and this is a solenoid, and we said that they are exactly similar in their magnetic field, and the reason is that there are currents in the magnet that we don't see because of the motion of electrons in the atoms, and there is a current in the solenoid like that. So when the solenoid is moved like this, the current is going down this way. So it's coming here and it's going down on this side, going up on the other side. The magnetic field is created like that. Usually we call this South Pole and North Pole. If you put your 4 fingers in the direction of the current around the solenoid, your thumb shows the north side. All right, this is how you can find the North Pole of the magnet. And then imagine you have a loop of current like this. So you see that the current coming toward you above in the upper side of the loop and going away from you in the lower side of the loop. And then if you put your 4 fingers in that direction, you see that N side, the north side. And if you put another one here with the same situation, south here, north here, and now you see that this current and this current are in the same direction. So what happens is that these attract each other. So therefore, you see that the north and south attract each other. Not because the north and south, there's something serious with them, it's because the currents now in this parallel direction. So when opposite poles are adjacent, currents are in the same direction. So they attract each other. Currents is the same direction, attract each other, therefore opposite poles attract. So if you put more of these, you see there's more current that are in the same direction, they attract each other, and you see that it corresponds to north and south being in the same, in the vicinity of each other, close to each other. All right, so, and now if you put 2 magnets, because they have the same virtual currents inside, the currents coming from individual electrons inside the individual atoms. And so they have the same current, they attract each other this way if the currents are in the same direction. It means that if the north and south are close to each other. And if you put one of them in this direction, the other one in the other direction, the currents are in opposite direction. Therefore, they repel each other. And therefore, that manifests itself by saying the north and north repel each other. It's because of basically the currents are being in opposite direction. So when like poles are adjacent, currents are in the opposite direction. Currents in opposite direction repel, therefore, like poles repel each other. So I hope this shed some light on why magnets behave like that. All right, any questions? All right. Now we want to calculate the magnetic field of a current in a circular loop of wire. If you have a circular loop of wire, this is like a circular loop, and if we see the cross section of it, the current is shown by a dot here by a cross, means that the current comes out of the page here, goes into the page here. All right, so it's going, if you look from above, it goes counterclockwise. And because of that current, each element of this loop creates a magnetic field like that, perpendicular to the radial direction, and comes from right-hand rule. You put your thumb in the direction of the current in that element that's coming out, you see that your fingers show circulating fields like this. So at this point, it is at that direction. And at this point, if you do the same, you see that at this point, the field it will be in this direction. So you see that the X component, or perpendicular to this axis, the components perpendicular to the axis cancel each other, and parallel components add up. And if you do the integral, it is easy to show that the magnetic field is mu naught I r squared divided by 2r squared plus z squared to the power 3/2. This is the magnetic field on the axis of a circular loop of wire or coil. So if there's only one turn of wire, if you have n turns, so the current becomes n times. All of them do the same thing. They create the same magnetic field at the same direction. So you can multiply that by n. For a coil with n turns, we have mu naught ni r squared divided by 2 r squared plus z squared to the power 3/2. So magnetic field is equal to mu naught I over 2r if you are at the center. When you are at the center, means z becomes smaller and smaller, becomes 0. If you put z equal to 0, what happens? If you put this equal to 0, r squared to the power 3/2 becomes r cubed. With one of these r with r squared cancels, you get 1r in the denominator. And if you have only one turn of wires, you have mu naught I over 2r. So you get this. So that comes from this equation, basically. Okay, and we define magnetic dipole moment of a coil as before, NIA. And B can be written in terms of NIA or mu. So it becomes mu. If you multiply this equation by pi and divide by pi, and if z is much larger than r, means that you're far away from the ring, so that you don't see the radius of it, you just see a magnetic moment, then r can be ignored here in the denominator, not the numerator, in the denominator, because you have a summation here, but that is multiplication. If you put that equal to 0, then everything becomes 0. But this is a approximation that's good because z is much larger than r, but r has some value. And so if you ignore the r squared compared to z squared, then you have z squared to the power 3/2 becomes z cubed in the denominator. And if you multiply by pi, you get 2 pi z cubed in the denominator. That's what you have here. And then pi r squared becomes the area times I becomes mu. Okay. And then you have mu naught mu. So mu naught over 2 pi mu over z cubed is the magnetic field of a small magnet of magnetic moment mu along the axis. All right. Any questions? All right. Magnetic field of a current in a circular arc of wire. So we have an arc of wire like this. Suppose it makes an angle phi from the center and it has a radius r. You want to see what is the magnetic field of this wire that carries the current I at this center. So it is easy to, again, do short integration and show that the magnetic field is mu naught I phi over 4 pi r. This is at the center of the arc. Okay. So it depends on phi. If phi becomes 2 pi, you have complete circle. And then if you put 2 pi, divide by 4 pi, you cancel the 2 pi, you get mu naught I over 2r, which is the same as what we had just here, mu naught I over 2 pi, 2r, right? So at any other angle, we have just fraction of that, because all of the magnetic fields of any element at this point are in the same direction. They are out of the page, right? So they are all in the same direction, therefore they add up like numbers, basically. And to find the magnetic field, you can put your thumb in the direction of the current and your 4 fingers show the direction that the field circulates around. And therefore at this center, it's out of the page. Another way you can use the right-hand rule, there's another way. You see that the current is going around the circle. If you put your 4 fingers around that circle, your thumb shows the direction of the magnetic field at this point. All right. Any questions? So there are two ways. In anywhere in physics, if something is going around and something is in one direction, you put your 4 fingers of your right hand in the direction of the thing that's going around. Your thumb shows the direction of the thing that's going in one direction. So here it could be a wire, in a straight wire that goes in current in one direction, and the field is circulating around. It could be a wire that's going around the field at the center is going in one direction. Either way, you can use your right-hand rule to get the direction of the field. All right. So now we want to introduce Amperes law. Amperes law is very similar to Gauss law, but it is different in the sense that there's a B dot ds. It's a line integral around a closed loop. In the Gauss law, we had the surface integral over closed surface. Here we have line integral over the surface, over the closed loop. And this equals to line integral B around any closed loop is equal to mu naught times the current passing through that loop. Here is the a statement that I got from one book, that book that I take a lot of stuff from. If we calculate the line integral of the magnetic field around a closed curve, the result equals mu naught times the total enclosed current. Means that the current that passes through that closed loop, closed curve, like this. Suppose there are 3 currents, I1, I2, I3. I1 and I3 are upward, and I2 is downward. And you assume this curve, this closed curve, and you integrate B dot dl, B due to any sources, not just due to these 3, the B through because of any sources. And then calculate B dot dl around this curve, one complete turn. Then the result the result will be mu naught times the total current in here. So here you see that this is the same curve, I1, I2, I3, and then I1 and I3 are going out of the page. Therefore, we're looking at this figure from above, top view, and I1 and I3 are coming out, I2 is going in, so the net current going through this loop is I1 minus I2 plus I3, I1 plus I3 minus I2. So this that goes in the opposite direction is counted as negative. And therefore, you see that in right-hand rule, your 4 fingers go around the curve in the direction of integration. Therefore, your thumb shows which direction current should be positive, should be considered positive, which direction should be considered negative. That's why, for example, in here, again, if you put your 4 fingers in the direction around this curve, outward is positive, inward is negative, okay? So if you're integrating it along in this direction, counterclockwise, outward is positive, inward is negative, therefore the result will be mu naught times this current. All right, this is Amperes law, and we can apply it to different situations. And in here, this is an example. If you have 2 currents, one I coming out, one I going in. So here it shows the magnetic field of these 2 currents and the L around the loop. You see that in this case, there are some places where B and DL are kind of in the same direction. In here, they are exactly in the same direction. Here are make an angle less than 90 degrees. Here also less than 90 degrees. So B dot ds, ds or dl. Here we have ds, here we have dl. I wasn't very consistent. Some of the material from another book. So you see that in this part, B and DL are making an angle less than 90 degrees. So B dot DL is positive. In the other side, B and DL making an angle larger than 90 degrees. Therefore, B dot DL is negative. So you see these have negative contribution, these have positive contribution. And the total becomes zero because the total current going through this loop is zero. All right, that is, you can conclude that from Amperes law. All right, any questions?
When doing Amperes law, are you not supposed to see now how you right now you only have positive current and negative current? And would we include the other positive current, or sorry, this is negative current, right? Would we include the other positive current as well, and then it'd still result as zero, no matter how much currents we have?
No matter how much currents are around. You see, this is, as I mentioned, in this case, the figure shows the magnetic field due to these two currents. But it doesn't have to be due to this current. No matter how much currents are around, the Amperes law says that for any closed loop anywhere in the world, there might be a lot of currents around. And if you calculate B dot ds from all the sources in the universe, you see that is not only because of this current enclosed. If you calculate that, it only becomes equal to mu naught times I enclosed. It doesn't mean that this B is because of this current. Okay, in this case it is, because they want to show you how this becomes zero. But in general, if the current is outside, it makes zero contribution to this integral. Okay, because the field is circulating around it, it makes a positive contribution on one side, negative contribution on the other side. So it gives you zero. The same as Gauss law that I explained. I don't know if I answered exactly your question or not.
No, yeah, that makes sense now.
Yeah, okay. All right. Now we can apply Gauss law to a special situation. This is Gauss law. This is the situation. We have a cylindrical conductor with the radius r, carries a current I that's uniformly distributed over the cross-sectional area of the conductor. I mean, this is the wire. It has a radius capital R, and we want to calculate the magnetic field at this distance r from the center, distance lowercase r from the center. And in this case, outside means r greater than r. My apologies. It should be the other way around. Outside means r is greater than r. I will turn back because I have several slides in this mistake. So if you're outside, then r is greater than r, and then you take a ds along, you take a Amperian loop. Remember, in the case of Gauss law, we used to get a Gaussian surface and apply Gauss law to it. Here, we take an Amperian loop and we apply Amperes law to the loop. So this is the Amperian loop. This is the circle, the red circle. And we take a ds along the loop, all right? And then we say because of the symmetry, B should be in that direction, all right? And then we say that integral of B dot ds should be equal to mu naught times I enclosed. And because B and ds are in the same direction, B dot ds becomes B times ds. And then because B, because of symmetry, is the same everywhere, B is constant for all of these ds's that you take at the different places along the loop. So B can come out. So it becomes integral of ds only, b integral of ds. The other side, the enclosed current is the total current of the wire. So it becomes like that. And integral of ds along this means adding all these distances, small distances together, becomes what? Becomes 2 pi r. So it becomes b times 2 pi r equal to mu naught I. And therefore, b, magnitude of b is mu naught I over 2 pi r. So this is the same as a long straight wire. Okay. This is the same as long straight wire. Again, this should be the other way around. Okay. And then we want to see what if we are inside the wire. Means that this lowercase r is less than r. This is, as I said, is wrong. This one is right. This one is wrong. Sometimes I copy paste something and I forget to change it. So this is now correct inside when r is smaller than the radius of the wire. And now we want to see what is the magnetic field at this point. We take an Amperian loop, which is circular and centered at the axis of wire. And then we apply Amperes law to this Amperian loop. This is the Amperes law. Again, we argue that because of symmetry, B should be tangential and also should be the same. There's no difference between this point and this point, or this point. Physically, there's no difference. So first we say B dot ds becomes B times ds. And then B is the same along any point on this loop. So it can come out of the integral. But what is the enclosed current? Enclosed current is not all the current. It is current times the area of this loop divided by area of the whole wire, because the current is uniformly distributed. So the current is proportional to the area. So becomes I pi r squared divided by pi r squared, and pi's cancel. And ds, again, integral of ds becomes 2 pi r with this r now. So becomes b times 2 pi r equal to mu naught I r squared over r squared. And you see one of the r's cancel. You can write it like this, mu naught I r divided by 2 pi r squared, because one of the r's canceled. All right, and then you can write this as mu naught I over 2 pi r times r over r. So that is the magnetic field of the wire at its surface. All right, mu naught I over 2 pi r. See, it's like a long straight wire at distance r, and that was like this when r is capital R, means that at its surface the magnetic field is this. And then multiply by r over r means that it changes linearly from 0 to the value at the surface as r increases from 0 to r. Okay, so you can write the magnetic field outside as that. You see, this is similar to the cylindrical shell theorem that we talked about. All right, so this is the magnetic field for this case when r is less than r. In this case, r is greater than r, means you're outside the wire. You're outside the wire, it acts like a long, straight, thin wire. When you are inside, it magnetic field changes from 0 to the value at the surface. If you want to illustrate that, it will be like this. First of all, the direction of magnetic field is always like azimuthal, means that tangent to the circle, like this. At this point is tangent to this circle, at this point tangent to this circle, at any point. But what is the magnitude of it? The magnitude is this outside changes by r, inside changes by r like that. So if you, from 0 to r, you see it changes linearly from 0 to the value at the surface. Outside is mu naught I over 2 pi r, means that it drops by 1 over r, 1 over the distance. Okay, And so it changes like this. So it has a maximum value that is at the surface. If you go farther away, it falls down. If you go in, it falls down. All right. So it's similar to the spherical solid sphere of charge we had, if you remember. All right. So this is magnetic field inside and outside of a wire that we can find easily from Amperes law. If you want to use the equations that we had directly to find that, it will be very difficult. It is possible, but it is very difficult to find this result. You need to do a lot of integrations. All right. Now, magnetic field inside a solenoid. Inside a solenoid, if you have an ideal solenoid, that is like all, you see that the currents are coming out of the page here and going into the page here, and it creates a magnetic field like that. You can apply Ampere's law to a loop like this, and you can get this equation. And this is a figure that shows that this is approximate. This mu naught Ni is this. But of course, because this is not infinite, it's not an ideal solenoid, it becomes less than that at the middle. If you go to the sides, it becomes even less than that. All right. So the question is, what if the solenoid is not ideal? The result of the answer to this question is not, I haven't seen personally in any books, but I want to actually derive it here. Suppose you have a short solenoid like this. Instead of a long, infinitely long one, you have a short solenoid. And this is the cross section. And you want to find the magnetic field at this point. This is a certain point in that, not in the middle, at any point inside the solenoid, but on the axis. All right. If you want to do that, you can put this coordinate system, let's call this Z and X this way. And this solenoid is from Z1 to Z2. All right. And then we want to see what magnetic field here is. So we need to integrate. At this point Z, we take a piece of this, a solenoid that has a length dz. And this one is like a loop of current. And that creates a magnetic field here. We know how to calculate the magnetic field. It calculates the magnetic field dB, and dB comes from this equation. Remember, for a loop is mu naught, the amount of current. This is called dN. Instead of N, we call it dN. With a certain number of current loops are in that dz. So we call it dN. I r squared divided by 2 r squared plus z squared to the power 3/2. This is the formula that we had. Instead of n, we put dn. Means that it is a small number of current loops in that dz. And how do we find dn? We said that for a solenoid, the number of turns per unit length is called lowercase n. I forgot to say that. N in that formula was the number of turns per unit length. So n is the number of turns per length of this part. So dn is actually n dz. So we can replace dn by n dz. So the formula becomes like this. So mu naught n I r squared dz divided by this. And this is the magnetic field created by this piece. And now we can integrate over the whole thing to find the total field. Oh, we need to integrate over z, from z1 to z2. So b is integral of dB, means integral from z1 to z2 of whatever is function of z here. All the constants are taken out of the integral, mu naught n I r squared over 2. All of these constants are taken out. we have integral from z1 to z2 of dz over r squared plus z squared to the power 3/2. And then we can do this integral. To do this integral, this is, anybody remembers from calculus how you do the integrals like that? You can go to the table of integral, or you can just practice by yourself. If you connect this line, you see that this z can be written as r times, z over r is tan of theta, or z over this distance, which is r squared plus z squared. You see this distance, this from here to here, is square root of r squared plus z squared. So that's what we have here. So if you take this change of variable, z equal to r cotangent of theta. So this is r, basically z over r is cotangent of theta, or r over z is tan of theta. Therefore, z over r is r cotangent of theta. And you could also write cosine theta. It will become like that at the end. So z squared is equal to r squared cotangent squared of theta by squaring this. And then z squared plus r squared is what? No, before that, dz is dz from here. If you take the differential, dz becomes negative cosecant squared of theta. Remember, the derivative of cotangent is cosecant squared with negative sign. So it becomes negative r cosecant squared theta d theta. And then r squared plus z squared. You see, this is z squared. If you add all squared, we get 1 plus cotangent squared of theta. Cotangent, 1 plus cotangent squared theta is cosecant squared theta. All right, so it becomes r squared cosecant squared theta, and therefore this r squared plus z squared to the power 3/2 becomes r cubed cosecant cubed theta. And now if we put all of these in the equation for dz, we put that negative r cosecant squared theta d theta. For the denominator, we put this. You see cosecant squared cancels, one of the r's cancels, and this cancels the other r. So it becomes mu 1/2 mu naught ni, r squared cancels, all of the r's cancel. And 2 of the cosecant squared cancelled, and 1 cosecant remains in the denominator, and that is inverse of sine with a negative sign. All right, it's negative, and 1 over cosecant becomes sine. So it becomes that negative sine theta d theta. An integral of negative sine, you know, is cosine, right? So it becomes 1/2 mu naught ni cosine theta evaluated between z1 and z2. And if you do that, you get 1/2 mu naught ni cosine theta 2 minus theta 1 if the theta 2 and theta 1 are these values. Theta 2 means the theta corresponding to z2, theta 1 means theta corresponding to z1. So if you consider the viewing angle of this edge from the axis to be theta 2 and viewing angle of the other end to be theta 1, we can write b equal to 1/2 mu naught and I cosine theta 2 minus cosine theta 1. All right, this is similar to what equation that I derived in chapter 22 for line of chart. So theta 2 and theta 1 and theta 2 are the viewing angles of the two ends of the solenoid from the axis as viewed from the field point. Field point is where we calculate the field. The source point are here. All right, so from this point, you see, okay, what is the angle of this one? What is the angle of the other one to the axis? Of course, when this becomes very, very large, you see that the angle goes to 0, but at any length of the solenoid, at any distance, it has some value. So you add, you use this theta 1 and theta 2, you calculate this, you get the B field at this point. And it has 1/2 mu naught Ni in front of it. So, okay, let's see some of the special cases. So let's put these up here. One special case is infinitely long or ideal solenoid that we already know what the answer is. In this case, it's like that. This is in every book. And in that, you see that if this becomes infinity, what is theta 2? Theta 2 goes to 0, theta 1 goes to 180 degrees, right? Theta 2 is 0, theta 1 is 180. And now if you put cosine of 180 and cosine of 0, you see that cosine of theta 2 is 1, cosine of theta 1 is -1. So it becomes 1 minus -1. You get a 2. With 2 cancels, you get mu naught Ni, which is the result that you can find from Amperes law. And as I said, this is in all books. You can find it in any book. But this result I haven't seen in any books. So this is what we expect. So it seems that the formula is working. The other special case is semi-infinite solenoid at one end. Means that you have a semi-infinite. This side goes to infinity. This side is truncated, and you're looking at it from this point. You want magnetic field at this point. In this case, theta 2 again is 0. Theta 1 becomes 90 degrees. The viewing angle of this side. When this becomes here, theta 1 is 90 degrees. So, and cosine of theta 2 is what? 1. Cosine of theta 1 is 0. So you get 1 minus 0, and then the result will be 1/2 mu naught Ni. This is also expected because this has a magnetic field half of the ideal solenoid, which is infinitely long solenoid. Half of the field is created by this side, half of the field is created by the other side. Now it's missing. So this is also expected. All right, and then another special case is short solenoid at one end. If you have a short solenoid and you are the field point is at one end, you have one angle that is 90 degrees, the other angle is some theta. Theta 2 is equal to theta, theta 1 is 90 degrees. And then cosine of theta 2 is cosine theta 1 is 0. So then you get this cosine theta minus 0. So you get 1/2 mu naught Ni cosine theta. And this is a new result that you can use. For example, in any case, you can split it into two of these. See, 1/2 mu naught Ni times cosine of this angle. And then for the other side becomes 1/2 and mu naught Ni times cosine of this other angle. And then you add them together. Of course, cosine of 180 minus theta becomes negative cosine theta. So it becomes like this. All right. Another special case is short solenoid at center. If you have a short solenoid, this is what the figure was showing. If you are at the center, you have these two angles the same, basically, or one angle theta 1 is 180 minus theta 2. So theta 2 is theta, theta 1 is 180 minus theta. And then cosine of theta 2 is equal to cosine theta. Cosine of theta 1 becomes negative cosine theta. And then here we get cosine of theta 2 minus negative cosine of theta minus negative cosine theta. We get 2 cosine theta. With this cancels, becomes mu naught Ni cosine theta, which is a new result that corresponds with that theory. Did you see that at the center of that solenoid, the value of the B field was less than mu naught Ni is because this cosine theta was, of course, less than 1. It becomes 1 when it becomes infinitely large. All right. Another geometry that we consider usually in this case is a toroid. Toroid is something like this. And the wires that go around a donut-shaped thing. And when the current goes into that, you see here, this is the cross section. The currents are going into the page at this point, coming out of the page at these points. And as a result, we have a magnetic field that's inside this toroid, like donut-shaped thing, but there's no magnetic field outside. The magnetic fields outside cancel each other perfectly. And the magnetic field inside can be calculated using Amperes law. You take this Amperian loop and say that integral of B dot dl is equal to mu naught times the current enclosed. And the magnetic field is parallel or tangential to this at any point. So B dot dl becomes B times dl. And then B comes out of the integral. And then the integral of ds becomes 2 pi r. So B times 2 pi r becomes mu naught times Ni. Ni is the total current going through this Amperian loop. Okay, because these are n wires. So if it has n wires and each one has a current I, the magnetic field is given by mu naught Ni divided by 2 pi r. So there's more magnetic field close to the center. Magnetic field increases as you go closer to the center. All right. Any questions? Toroid is used for magnetic fields like that. I don't know exactly. To create a magnetic field inside a donut-shaped space, but there's no magnetic field outside of it. So when they want to make an experiment that has only magnetic field at one point and not anything at the other, they use this kind of shape. All right. These are the formulas that you have in this chapter. And so again, you see this is the magnetic field of a moving charge. This is magnetic field of a piece of wire at the distance r from one end, and viewing angle of the other side is theta from the perpendicular direction. This is magnetic field of a long straight wire carrying current I at the perpendicular distance r. This is Amperes law, magnetic field of an element of current. This one is magnetic field of a coil of n turns along the axis at distance z from the center. And this is the this one when z is equal to 0 means at the center, and we have only one turn of coil. This is for an arc like this, but not a complete circle with the angle phi. If the angle is phi, not 2 pi, then it has phi over 2 pi of that circle. This is Amperes law. This is the, again, the same thing for a long, straight, cylindrical conductor carrying current I. Outside acts like a thin wire of current I. Inside, it is like this. It increases radially from 0 to the magnetic field at the surface. Here is for the ideal solenoid. Here is for the toroid. Of course, the results that I calculated for different kinds of solenoid, finite solenoid, is not here. All right. So these are basically all you need to know in this chapter. Formulas are here. So let's see how we can use them to answer some question. Any questions so far? All right. Here says the figure represents a snapshot of the velocity vectors of 4 electrons near a wire carrying current I. The 4 velocities have the same magnitude. Velocity V2 is directed into the page, see as shown by the crosses. Electrons 1 and 2 are at the same distance from the wire as are electrons 3 and 4. Rank the electrons according to the magnitude of the magnetic forces on them due to current I greatest first. What do you think? Any ideas? So this current I creates a magnetic field, and magnetic field applies the force in a moving charge. So these electrons that are moving experience a force. We want to rank the electrons according to the magnitude of the magnetic forces on them due to the current I. Any ideas? All right. First of all, the magnetic force, remember, was the first circulating around the wire. So it's coming out above the wire and it's going into the page below the wire everywhere. So this is the direction. The magnitude of the magnetic field of the wire is mu naught I over 2 pi r. Means it depends on the distance. So if the r is smaller, the b is bigger. So b for 1 and b2 are the same. For this first electron and second electron, b is the same because r's are the same and smaller. And this one is greater than for b for the other two. b3 equal to b4. So we have b's are related like that. And then velocities are the same magnitude, but they have different direction. And you see that this one is moving in the direction of the B field. And remember, the force is Q V cross B. Means that if V is in the direction of B, there's no force. So F2 is 0. And for these 3 and 4, because they are in the perpendicular direction to the magnetic field, you can see, you can use your right-hand rule. Say F4 is in this direction, and F3 is in this direction, and F1 is also going this way. If you use V cross B, oh sorry, these are electrons, so the directions are opposite because they are electron. So V cross B is that direction. V4 cross B is to the right, but because it's electron, it will be in this direction. So F4 is in this direction. F3 is also opposite. If you do V cross B is down. So the force, which is Q V cross B, will be up because it is negatively charged. All right. And you see that F3 and F4, everything is the same. V is the same, Q is the same, B is the same. They have the same magnitude of force. So F3 is equal to F4 in magnitude. But they are in different directions. And V1 is the same as the other ones, but this electron, the first electron, is moving in a larger magnetic field. So it has larger B, therefore F1 is greater than F3 and F4. And then these are larger than F2, which is 0. So this is the ranking. All right. Any questions? So first we need to figure out which direction the magnetic field is at the position of each one of these electrons. And then what is the magnitude of the magnetic field, and then how they are oriented, the velocities are oriented with respect to magnetic field, and then figure out which one has more force acting on it. All right. Now, this figure shows two long straight parallel wires that are 1 meter apart. The wire on the left carries a current I1 of 6 amps into the plane of the paper. So as you see, the I1 is 6 amps that going into the page. Therefore, it's denoted by a cross. A, what must the magnitude and direction of the current I2 be for the net field at point P to be 0? This is point P. We want the field of this current I1 and I2 to be 0 at this point. Then what are the magnitude and direction of the net field at Q? Then what is the magnitude of the net field at S? So these are many questions. Magnitude, what is the magnitude and direction of the current I2 first? We want to see whether this current is into the page or out of the page, and how much is it? So I broke this into several small questions. First, what is the direction of the magnetic field B1 of the current I1 at point P? At this point, what is the magnetic field of this current I1? Is it A, B, C, D, or E, or F? Anyone?
Is it A?
Why is it A?
Because you put your 4 fingers inside the direction of the current and then it's pointing to the left? Or
No, this is a long straight wire. Do you understand that? It's a long straight wire. It's perpendicular to the page, and the current is going into the page. What did we say about how to find the direction of the magnetic field of that current? We put the thumb in the direction.
oh yeah.
The current. You put your thumb in the direction of the current, and then your 4 fingers shows which direction the magnetic field circulates around the current. So if you put your thumb in that direction, you see that the field is circulating like this, right?
Right.
So means at any point it's circulating like this. So at this point, and at any point is tangent to that. So at this point is tangent will be this way. All right. So let's. I have some more figures that clarifies this idea. Yeah, you see, this is the field that the field of the magnetic field of a current that's going into the page. Remember this figure I showed you? You put your thumb in that direction into the page, and your 4 fingers shows this circulating field. What we mean by that is that the magnetic field at any point is tangent to these circles. Means at this point, the field is this way. At this point, the field is that way. At this point, field is this way. At this point, field is that way. Does it make sense? So at this point, therefore, if it is perpendicular to the radial direction always, and just that right-hand rule shows which direction. See, perpendicular to this radial direction could be this way, could be this way, right? This right-hand rule shows that it should be the one that's going down. So the answer is D. All right. Does it make sense? Any questions? So see, sorry, but the field is like this. At any point, it is perpendicular to the radial direction. When you go perpendicular distance away from the wire, right? Means like this. All right. So we get to this. Now, another question. Now we know that this is the magnetic field of I1 at this point. Now I want you to focus on I2 for the net B, field to be 0 at point P. What should be the direction of the magnetic field B2 of the current I2? Which direction should it be? So that the net field at P becomes 0.
It's the opposite direction, which is B.
B, very good, yes. So the answer is this. The other one has to be in this direction so that the magnetic field is 0 and should be in the same magnitude, right? So the answer is B2 has to be in this direction and the same magnitude, and cancel it exactly, okay? So for the net B field to be 0 at point P, should the direction of the current I2 be into the page or out of the page? What do you think? Yeah, Tanat said out. Everybody agrees? How do we find that? We said that if the field at this point is this way, yeah, everybody says out. Very good. So if the field at this point is up, means that the field is circulating around I2 like this, right? It's circulating like that in this direction. So if you put your 4 fingers in that direction, your thumb shows up, means out of the page. So I2 is out of the page. Okay. Very good so far. And then we want to see, okay, what is the magnitude of I2? So we say B1 is mu naught I1 over 2 pi R1. All right, R1 is this distance, right, from current 1. It's R1. This one is R2, right? The distance from the wire 2. So B1 is 4 pi times 10 to the negative 7 times current 6, I1 is 6, divide by 2 pi times R1. You see R1 is 1.5. So do 2 pi cancels, you get 12 divided by 1.5 times 10 to negative 7, so it becomes 8 times 10 to negative 7 Tesla. And B2, which is mu naught I2 over 2 pi R2, should be equal to that. So we put that equal to for B2, and then the result should be this 8 times 10 to the negative 7 should be equal to 4 pi times 10 to the negative 7 I2, which we don't know, we want to find, divided by 2 pi times 0.5. And then we solve, so 2 pi cancels here, we get a 2 here. 2 divided by half, 10 to the negative 7 cancels. 2 divided by half becomes 4. So 8 becomes 8 equal to 4 I2. So I2 becomes 2. I2 becomes 2 amps, right? So we found I2. Now we what must the magnitude and direction of the current I2 be for the net field at P to be 0? We found it. And B, then what are the magnitude and direction of the net field at Q? So we want to find the net field at this point. Again, now we know the currents and directions. what is the direction of magnetic field B1 of the current I1 at point Q? Can you tell me?
B
What is,
out up.
you said B up? Yes, very good. So B it this way because you can put your thumb in the direction of the current and you see that the field is circulating this way. So it means that at this point is up, at this point will be down, at this point will be this way. At any point is different, but at this point, Q will be up. All right. Okay, so let me get rid of these. All right. And then what is the direction of magnetic field B2 of the current I2 at point Q?
It would be the opposite. So D.
Yes, D, very good. So again, you put your thumb in the direction of I2 and the field is circulating in counterclockwise direction. So again, at this point also counterclockwise, so we'll be down. So it will be like this. Of course, B1 is bigger because I1 is closer and is bigger. So we can we have a net force, net magnetic field upward. So net field will be B1 minus B2 in magnitude. So this is B1 and B2 mu naught I1 over 2 pi R1 minus mu naught I2, sorry, I2 over 2 pi R2. So it becomes mu naught over 2 pi can be factor. Mu naught over 2 pi times I1 over R1 minus I2 over R2. So becomes 4 pi, this is mu naught, 4 pi times 10 to negative 7 divided by 2 pi times 6 over 0.5 minus 2 over 1.5. All right. So B becomes, this is like 12 and 1/3. So it becomes 21 point. Oh, is the 2 factor here also? So it becomes 21.3 microtesla. And micro is 10 to negative 6. So I don't know if I did it right here. So there's a 2 factor here. It becomes 12 times 2 becomes 24 minus 4 minus 4/3. 24 minus 4/3 becomes 20. Yeah, I think it's because the 10 to negative 7. 21 times 10 to negative 7. So that should be 2.13, I guess. 2.13 microtesla. Anyhow. So anyway, you can calculate that. The value is not very important. All right. And now we want to find, this is the magnitude. Magnitude, of course, the direction is up because the upper one is bigger. So B net is upward. What is the magnitude of the net field at? Oh, I'm out of time. Sorry, I didn't notice the time. We continue from here next time. If you have any questions, I'll be here. If not,
Have a good day, Professor.
you
Have a
too.
nice day, Professor.
Sorry about overtime.
That's all right.